All right, we've defined the matrix inverse and talked about how to work with that thing and how to figure out what it is. We're going to now talk about something called the determinant. Because we're talking about how we take a matrix and we fill in an augmented matrix, put the identity matrix here, and put it in reduced row echelon form, and then we decide whether or not the inverse exists. It would be nice if we could figure out if the inverse exists before we went to all this trouble. So what can we do? We're going to define something called the determinant for a 2x2 matrix. And then I'm going to basically define it in general. I'm not going to go through and derive the method because it's really technical and very involved. And we're basically just going to build on what the intuition we get from a 2x2 matrix. So the idea is this. I want to solve a system of equations where the system is made up of a matrix is equal to an unknown vector is equal to a known vector. I would like to know, does A inverse exist? If I were to put this in an augmented matrix, suppose the matrix A is made up of entries A, B, C, D, and I've got some numbers for B. I actually don't really care what B is. I only care whether or not I can figure out if this inverse exists. Well, if I put this in reduced row echelon form, what can I do? Let's not do the normalization where we make A equal to 1, because if A is 0, this is going to break down. But notice, if I take minus C times row 1, I'll get minus AC here, and add A times row 2, then I will get what? Minus AC plus AC is 0, and I would get a 0 there. What will happen here is I get minus BC plus A times D. So let me write that as AD minus BC. And I'm going to get garbage here. I don't care what that is. If I want to put this in reduced row echelon form, I can only do this if that number is not 0. If that number is 0, right, I'll get zeros in that bottom row, and the matrix inverse will not exist. So this term AD minus BC, this indicates whether or not the inverse exists. If it equals 0, there's no inverse, or we say the matrix is not invertible. If AD minus BC is not 0, the inverse exists, and we say the matrix is invertible. So that quantity right here is extremely important. And so for a 2x2 matrix, we're going to define that to be the determinant. So for a 2x2 matrix, we say that the determinant is AD minus BC, where the matrix, the top row is AB, and the bottom row is BD. Let me rewrite that because I made a mess of it. So if I have a matrix A, first row is AB, second row is CD. The determinant of A is AD minus BC. And you can think of this as I'm going to multiply the diagonals going that way, and then I'm going to subtract multiplying going that way. And if this is 0, then A inverse does not exist. If the determinant of A is not equal to 0, A inverse exists. And the notation is, so we don't really like writing out determinant of A every time. So we just write it like this, and it looks like absolute values, but it's not. Okay, and what the key thing here is this is a matrix, and we're taking the determinant with using this notation. So for example, the determinant of a matrix 2, 3, minus 1, 1, we already know that inverse exists, but we go across the diagonals this way, so we get 2 times 1, then we're going to subtract going the other way, 3 times a minus 1, that's going to be 2 plus 3 is 5. Because that's not 0, we know this matrix is invertible, and that gives us a license to go try to find that inverse. Okay, we can generalize this for larger matrices. And again, because this is about inverses, this has to be a square matrix. I'm just going to state how we do this. Again, the proof of this is very technical and not very interesting. So I'm going to assume it's an n by n matrix. So we have n columns if we go across the first row. And then for the second row, I'm going to have entries across. And then if I go down to the ith row, I'm going to have row I, so I have column 1, column 2, then column j. So this is row 2. So this is row I, column n. I go down to the very bottom row, I'll have row n. Have column 1, 2, column j, and column n. And I can just do this. And I'm going to focus on column j and row I. And the idea is now if I remove column j and I remove row I, I'm going to have a matrix with one less row and one less column. I'm going to call that a new matrix. I'm going to call it M sub I j. Okay. And I'm going to use this to find the cofactor of a matrix. The cofactor of a matrix A is going to be found by removing row I and column j and taking the determinant of what remains. I got to be a little careful here, as I'm going to have to multiply by a minus 1. And that's going to be the determinant of the matrix A after I remove row I and column j. And we're going to define the determinant of a square matrix to be the sum across any rows of the entry in that row and column times the associated cofactor after I remove that row and column. And notice this is, it turns out I can pick any j that I want. Okay. So this is really confusing and really ugly notation, but when you see it in action, it's not so bad. So for example, suppose I have b is 3, 2, minus 1, 4, 6, 2, 1, 3, 1. And it turns out I can pick any row or any column and expand that way. There are no zeros anywhere, so there's not going to be any advantage. So I'm just going to go across here. I'm going to take out 3, and what is left afterwards is going to be that thing. Then I'm going to take out the 2, and after I remove that row and that column, I'm going to be left with 4, 1, 2, 1. And then I am going to take out that last column, that first row, And what's left after I remove that row and that column is going to be that thing. So let's see what that looks like when I go through and actually do it. So what did I say? I said B is 3, 4, 1, 2, 6, 3 is 1, 2, 1. Okay. The determinant of B, again, I said I'm going to go across that top row. So the first entry is 3 times the determinant. If I remove that top row in that first column, I'm left with 6, 2, 3, 1. Now notice this is row 1, column 1. So minus 1 raised to the 1 plus 1 is going to be minus 1 squared is 1. Now when I take the 2, this is row 1, column 2. So that's minus 1 cubed, so that's going to be minus 1, so I'm going to have to subtract. If I remove that top row and that middle column, I'm left with 4, 1, 2, 1. Then finally, I've got the minus 1. Now this is row 1, column 3, so 1 plus 3 is 4, minus 1 to the 4 is positive. Now if I remove the top row in that column, I'm left with 4, 6, 1, 3. And then what's nice about this now is I have a 2 by 2 matrix, 2 by 2, 2 by 2, and I can just now plug into the definition of the determinant for that. So that's going to be 6 times 1 minus 2 times 3. Now I'm going to have 4 times 1 minus 2 times 1. And here I'm going to have plus a negative 1 times 4 times 3 minus 6 times 1. And now I just got to grind this out. So this is going to be 3 times 6 minus 6 minus 2 times 4 minus 2 plus a minus 1. So that's going to be 12 minus 6. So that's 3 times 0 minus 2 times 2 minus 6. So I'm going to get 0 minus 4 minus 6 is minus 10. So B is an invertible matrix. Let's do another example. Suppose I have the matrix C is 4, 3, minus 1, 0, 1, 0, 1, 7, 0, 1, 2, 6, 2, 0, 3, 2. Okay, I see some zeros in here, so I'm going to like multiplying by 0. So I'm going to choose either a row or column that has the most zeros. And that has the most zeros. So what I'm going to do is I'm going to go down this way. Notice it's going to start with the 3. That's row 1, column 2. So minus 1 to the 1 plus 2 is going to be minus 1 cubed is minus 1. This 0 is row 2, column 2. Minus 1 to the 2 plus 2 is minus 1 to the 4th is 1. That 1 is row 3, column 2. So minus 1 to the 3 plus, column 2. 3 plus 2 is minus 1 to the 5th is minus 1. And that 0 is row 4, column 2. So minus 1 to the 4 plus 2 or minus 1 to the 6th is 1. All right, so for the determinant of C, it's going to be 3 times the determinant. So I got to be careful, minus 3. If I remove the first row in that column, I'm left with 1, 0, 2. And then I'm going to have 1, 2, 3, and then 7, 6, 2. For this term, I'm going to have plus 0 times the determinant. So if I remove that row and that column, because I've got that 0, I'm left with 4, 0, 2. And then I'm going to have minus 1, 2, 3, then 0, 6, 2. But note, it doesn't matter what that is. It's going to be multiplied by 0, so I can just toss it. Now for that one, that's going to be a minus 1 times. So if I remove that row and that column, I'm left with 4, 1, 2. I'm going to have minus 1, 1, 3. I'm going to have 0, 7, 2. So I've removed that row and that column. Finally here, I'm going to have plus 0 times the determinant. So if I remove that row and that column, I've got 4, 1, 0, minus 1, 1, 2, 0, 7, 6. And again, 0 times that, I don't care what they are, it's just going to be 0. So this determinant is going to be 3 times the determinant of 1, 1, 7, 0, 2, 6, 2, 3, 2, minus 1 times the determinant of 4, minus 1, 0, 1, 1, 7, 2, 3, 2. Is that correct? I think that's okay. Oops, something, I forgot the minus. Something's wrong. So with this 3, I remove the first row. I'm left with 1, 1, 7, 0, 2, 6, 2, 3. I think that's okay. This came from that term. So if I remove that row and that column, I'm left with 4, 1, 2, minus 1, 1, 3, 0, 7, 2. I think we're okay. All right. So now I've got the determinants of 3 by 3s. Let's see. I like that row because there's a 0 there. And I'm basically starting over. Now notice because I've got I'm basically just increasing each row or column each time. This would have been, if I would have gone across that row, it would have been plus, minus, plus, minus. If I'd gone across there, it would have been minus, plus, minus, plus. Across there, it would have been plus, minus, plus, minus, then minus, plus, minus, plus. So I went minus, plus, minus, plus. If I'm going to go across this row, this would have been plus, minus, plus, which means this would have been minus, plus, minus. So leave the minus 3 alone. This is all going to be times minus 0. If I remove that row and that column, I'm left with 1, 7, 3, 2. Here is going to be plus 2 times. If I remove the middle column in that row, I'm left with 1, 7, 2, 2. And then for the 6 is going to be a minus 6 times. So getting rid of that column, that row, I'm left with 1, 1, 2, 3. And I can deal with that later. So minus 1 times quantity. All right. I'm going to want to go with that column. Reason being is I want to try a column just for fun, and there's a 0 there. So let's see, this would have been plus, minus, plus. So that's going to be plus, minus, plus. So I'm going to have plus 0 times. If I remove that row and that column, I'm left with 1, 1, 2, 3. This is going to be minus 7. So if I remove that row and that column, I'm left with 4, minus 1, 2, 3. Removing that row, that column and that row, I'm left with 1. Oops, I gotta be careful. Plus 2 times. So I'm with this 2. I'm removing that row and that column. 4 minus 1, 1, 1. Ooh, so determinant of C I decided was minus 3 times minus 0 times the determinant of 1, 7, 3, 2. Plus 2 times the determinant of 1, 7, 2, 2, minus 6 times the determinant of 1, 1, 2, 3, minus 1 times the determinant of 0, 1, 1, 2, 3, minus 7 times the determinant of 4 minus 1, 2, 3, plus 2 times the determinant of 4 minus 1, 1, 1. So that doesn't matter. It's got zeros. That doesn't matter. It's got zeros. These, I can now just use the definition for determinant of 2 by 2. So this is going to be 2 times 1 times 2 minus 2 times 7. So it's 1 times 2 minus 2 times 7. Minus 6 times 1 times 3 minus 2 times 1. Minus 1 times the quantity, so I'm going to ignore that. Minus 7 times 4 times 3 minus 2 times minus 1 plus 2 times 4 times 1 minus 1 times minus 1. What a horrible mess. So this is minus 3 times 2 times 2 minus 14 minus 6 times 3 minus 2, close, minus 1 times, so I got a minus 7. This is 4 times 3 is 12, minus a minus 2. This becomes 2, that becomes 4, minus a minus 1 is 4 plus 1. So I have minus 3. I gotta be careful, that was a parentheses. So this becomes 2 times minus 12. Minus 6 times 1. This becomes minus 1. This is minus 7 times 14 plus 2 times 5. So this becomes minus 3 times minus 24 minus 6 minus 7 times 14. It's going to be 98. So it's minus 98 plus 10. So I get minus 3 times 24 is minus 72 plus 18. This becomes plus 98 minus 10. So what's 98 minus 72? That's 26. Then 18 minus 10 is plus 8. So the determinant is going to be 34. All right, so C is invertible. Just a quick note, and I probably made a mistake in there somewhere, so you should double check that. There's a couple important properties of determinants. One is if I have a matrix A times B and I take its determinant, it turns out that's the same thing as the determinant of A times the determinant of B. And that immediately gives you a very nice result. You should be able to show that the determinant of an identity matrix is 1. So that'd be a good quiz question. If I want to take the determinant of A times A inverse, I know that's the same as the determinant of I, which is 1. That means the determinant of A times the determinant of A inverse is 1. So the determinant of A inverse is 1 over the determinant of A. And I know that exists because if A inverse exists, the determinant of A is not 0.